as well as those, so there's another kind of fluid, which isn't really, in a sense, really a fluid at all, and that's something like mayonnaise. I'm sure you've all seen mayonnaise before. Online. So mayonnaise is actually, strictly speaking, a solid. If I take a piece out, I'll just put it on the floor. And you can see it actually doesn't fall under gravity. So it's actually a solid if you, in the strict sense that it retains its shape. However, of course, it's quite soft, so you can spread it very easily. In fact, it's much easier to spread than something like honey, which is a true fluid. And again, to prove it's a solid, notice that you can still see where the knife mark was. So again, it's a solid because it requires a certain amount of stress before it flows, but once you've exceeded that stress, it will then flow quite easily. And again, you can put that on this graph because you can see that in a sense what you have now is you have to apply a certain amount of stress to get it to move at all, but once you've applied that, then again, in fact, it will tend to shear thin over like that. That's roughly what mayonnaise looks like. And there are lots of other materials like that. Toothpaste is another example. Again, toothpaste will sit on your brush, but obviously it will break up when you actually start brushing your teeth. And a lot of, in the personal care industry, it's all about getting those things right. So you have the right kind of product rheology or properties for what the consumer expects. Okay. So that's actually quite a simple kind of non-Newtonian behaviour. There are actually some far more interesting ones, which are fluids that have memory. So here's an example of this. This is a silicon polymer. It's normally sold as silly putty or theraputty. I'm sure how many people have seen silly putty? There's quite a few of you. So one thing you know about silly putty is it's a liquid. Look, it's adopted the shape of this container. It's got a nice flat surface. It's slightly on a tilt because it's been on my bag. I'll get it out here. But it feels very much like an elastic solid. And in fact, if you roll it into a ball, you can bounce it on the table. There you go. And what's more, if you grab it and pull it apart quickly, it snaps. Again, just like a solid. However, if I do things on a much slower time scale, so if I draw this now the same way, but much more slowly, you can see it just keeps going and going and going, forms what's called ductile fracture, so it's much more like a liquid. So you can see the way it behaves depends very much on how fast you do something to it. So it has an internal clock, it has some kind of memory of what's happened to it. And in fact, if we put it on the end of the table, to see what happens with this. Then over a course of probably longer than I have for this talk, it will actually pour down over the edge of the table like that. So it is a true fluid, but it's a fluid on very long time scales, but a solid on short time scales. Okay, so how can we put that into mathematics? This is my worst equation, the whole talk. So we said before in Newtonian fluids we wanted the stress to depend on the shear rate, but now we have to have something that depends on not just the current shear rate, but on all past shear rates. And so what you do is you combine that into an integral. So you have a stress as a function of shear rate, and there's what used to be the viscosity is now replaced by a function, which is called the relaxation time. And it's this thing which tells you all about its memory. So here's here's g of t, and it typically looks like this. And so there's a certain characteristic time over which the fluid forgets. So a viscous fluid is going to be something which forgets immediately, and an elastic solid is something that always remembers what happened to it because it knows to go back to its original shape. So these materials lie somewhere in between. And you can show more that if I think about something that happens very quickly so that g doesn't change very much, then you can essentially pull g out of this integral, in which case what you're going to end up with is just the integral of the shear rate, which is the amount of strain you've applied. So that's what you would have for an elastic solid. On the other hand, if you go the other way, then you end up with something where you have, if you go over a very long time scale, so that the shear rate isn't changing over the period of time of which G relaxes, then you're going to recover the viscous liquid. So within this equation are all possible models between elastic solids and viscous liquids. It should be said that this doesn't have shear thinning built into it. So this one has a constant shear viscosity. So this model doesn't give you the things I showed you before. But it does at least capture some of that elasticity. So you might ask the question, well, where is this memory coming from? It doesn't seem natural that a fluid should have a memory. We think of memory in terms of solids, as I said, elasticity, where solids remember their original shape. So why have these fluids got memory? So here's another memory fluid, known locally as red goo, whenever we want to borrow it for experiments. So this again looks like a liquid, but it has memory because I can pour it and it goes back into the container. Shall I do that again? So you pour it out, there's a point of no return, and then it will go back into the container. So what is that? Well, that's a fluid. It's essentially this same corn syrup, but I've added to it a small amount of polymer. Now, polymers are very, very long molecules. And essentially what happens is that when you, in a flow, these polymer molecules that behave rather like strings, and they get stretched out. And they don't like being stretched, they want to be back in a ball, and so they then relax back, and this relaxation takes place over a period of time. It takes them a while to come back, and that's what determines their memory time. Now, if we linked all the polymers together, you get a rubber. If you join them all together, because they're free and they can move around, then you still have a liquid. And this slide here is an experiment done on some giant molecules formed by taking DNA. In fact, taking DNA and splicing it together to get a very, very long strand, big enough, in fact, so you can see it, or you can see the fluorescence it produces, so you can actually see this polymer actually stretch in the laboratory, and down here is a computer simulation. Now, these DNA experiments were done by a man called Stephen Chu, who's a Nobel Prize winner from Stanford University, and he's now Barack Obama's energy secretary. So this shows you where you can go with slime science. Okay? You can go all the way to the White House and having to cure the world's energy problem. So he's got a bit of a task on his hand. Okay. So now you've got an elastic material. So this is this elastic material. Let's try and do some other fun experiments with it. Now, when you stir a glass, because some water. When you stir water, then it goes down in the middle because of centrifugal force, as we heard in the last lecture. So what happens now if I stir this fluid?